All right, hello everyone. I see we got a few people in here already. So, welcome to the new format of class. And if you haven't seen, TCC has announced that we're going to be running things this way for the rest of the semester. It's crazy times that we're living through, and we're going to make the best of it as we can. And before we continue on to where we left off in 2.2, I just want to point out a few things. Also, I am leaving text chat open, so if there's ever an issue you can't hear me or my screen isn't being shared, you can point that out over there. I'm not necessarily going to have a lot of time to take questions during these lectures. Unfortunately, you can always email me. I'm setting up a discussion or several discussions ultimately in Canvas for things. But homework is still going to be due on test days for the most part because test one was really extended due to everything. I made that homework due last night. And please remember that test one is due tonight. I only have 10 people's tests, which is a little more than half. But I want to make sure that everybody gets a chance to take the test. It's been available since last Wednesday. That's 6 days. That is more than enough time. So remember, you get 2 attempts on that. I'm taking your best score, and there's no password for it. You are still supposed to be doing it without your notes and without calculators, and just make the best of it. Whether or not I can control that, I know, there's issues there, but remember that all of this material, maybe not all of the material, but most material that you see in Pre-Calc 1, you're going to end up seeing again in Pre-Calc 2, you're going to end up seeing in Calculus, whether you take the business version of it or the heavier STEM version of it. Also, please note that my math lab, I've had a couple people email me and say, it's not working for this hour or that hour. So please don't just wait to the last second to do your homework. I know y'all have heard me say this a million times, but there's a lot of sites being overloaded. I've heard some people having issues with Zoom every now and then, and this is why I'm recording my lectures. Technically, attendance is supposed to be through the live recording, but I'm not necessarily going to hold people to that unless they're not doing their assignments. As you know, I'm pretty lenient with things, but don't just think that you can just skip watching the lectures. Most people are not going to be able to interpret this on their own without the lecture. So if you can't catch it live, remember that I am going to set up links after a session is done in Canvas. It'll be right under where it says live recording. I'll have the date on it. I'll have the sections that it covers, and it'll link right to YouTube. And you can even find under my playlists on my YouTube channel the other videos as they are created, since this is our first one. So just as a notice ahead of time, test 2 is going to be on chapter 2. I'm going to keep it the same format as test 1 for now. If I think that's going to change, I'll let you know, but I don't anticipate that. The review will be sent out either as a PDF in your email, or I might just make it a MyMathLab style assignment for you to be able to work on up there. Once we finish the chapter's material, and then the test will be available for several days, just like test 1. Not necessarily a full week. That was a bit of a different circumstance since classes weren't in session. So I'm thinking 2-3 days is generally how long I'm going to have a test up. So again, check Canvas for your live videos and recordings. Discussion board on Canvas, I was just setting that up before getting here. Also, I am likely gonna do some quiz questions, maybe kind of as like a homework grade. I haven't decided exactly what I want to do with this, but I want to hold people accountable to watching these videos. So there might be like a random question, 15 or 35 or 70 minutes into the video, and I'll go, all right, here's today's quiz question. And then I'll post a spot in Canvas for you to answer that. And it'll be super easy. It's basically just going to be, did you watch the video? And I'm not going to tell you when it is in the video. I'm not even going to tell you if there's a quiz question at the beginning of the video. You have to watch the lectures. So please watch these lectures fully. And I think I already said chapter 2's homework is going to be due the last day of test 2. All right, so let us, here we go. Continue where we left off in 2.2. We already talked about increasing, decreasing constant for functions. We said that a function is increasing. If you move right, you're going up, so something like that. Or decreasing if as you move right, you're going down. Or if as you move right, it's flat, that would be constant. We said to always use parentheses for the interval notation for increasing and decreasing, and we gave the logic behind that in class. And we said to always make sure you're using the x values, never, ever, ever the y values. So the next thing we want to talk about is relative extrema. Relative extrema, also known as relative maxima or minima. And these words kind of sound like maximum and minimum, because guess what? That's exactly what they are, but they're the plural version of maximum and minimum. So there can be more than one maximum relative to an area and more than one minimum relative to an area. So we're not saying it's the absolute max or the absolute min. We're not saying it is the highest point or the lowest point overall. We're saying it's the highest point in a region or the lowest point in a region. So let me just kind of on this screen scribble some stuff over here. Let's go red actually. Actually, you know what? Let's clear that. Get my writing tablet back out. There we go. So here's just a random graph I got over to the side. And there are a couple points of, ooh, that's a bad color. I thought I hit a different one. And that's green. That might not be good for the colorblind. There's a couple of points of interest here. And I am highlighting them right now, or darkening them, that is to say. Those points are the relative extrema that we're talking about here. So a relative maxima is any point that is higher than the points immediately to its left and right. So I want you to imagine that you took your nose and you sat it right around this point right here, this left dot. And if you took your nose to your computer screen or your phone or whatever, to the board in theory, and if you put your nose right there, you wouldn't be able to see anything to the left or right of the area I'm kind of circling right now. You would only really be able to see this region right here. And in that region, it is the highest point. That's what we mean by a relative extrema. In just the central location of that point, if you go a little to the left or a little to the right, it is the highest of those points. The same can be said here. If you put your nose to that point, you would only be able to see about that much around it, and it's the highest point in those regions. So those points are relative maxima. On the contrary, these 2 points down here, if you were to say, put your nose to them, and you were only able to see around, about this much. If you look a little to the left and a little to the right, all those points to the left and the right are higher. This is the lowest point just in that little teeny region. This is the lowest point just in that little region. So those points are relative minima. Now, there's nothing that says a graph has 2 relative maxima and 2 relative minima. It could have 40 relative maxima. It could have 1 relative maxima. It could have no relative maximas. But the trick is you're looking for these little hills and valleys. You're looking for peaks and troughs, if you will, if you like those words, hills and valleys. So any point that's at the top of a hill is a relative maxima. Any point that it's at the bottom of a hill, it's a relative minima. Now, there is specific language that we have to use for this. We talk about where the point is located at and what it actually is. And a lot of students will get these backwards because they don't either learn the language or maybe they just flip a coin at the last second. The location is the x value. Just like when we talked about things increasing and decreasing, that has to do with the location of something, and that's the inputs, that's the domain, that's the x values. So when I ask you where a relative extrema is located at, you have to say the x value. If I ask you what the actual max or minima is, that means the y value. That says, what do you actually get out of this when you process the input? What's the output? The output is the max or the min. All right, so let's try this out. Let me clear my screen, and I have to clear my screen whenever I want to do something else, just so you know. And that's what I mean by clear the screen. Pull up a whiteboard. And let's get to example 2. We did example 1, which was having to do with the increasing, decreasing constant stuff. What feels like forever ago. Oop, example 2. I said it and then I wrote the wrong thing. Find all, let me switch this to text. Find all relative maxima, minima, where they are located at. So for A, let's make a little graph here. And I will do the best of my abilities. I'm still getting used to this drawing tablet. You already know how my handwriting is in general. So do what we can. So I'm going to have this point right here. And then to the left of it, we're going to go up. To the right of it, we're also going to go up. And I'm going to have the height of this point be -8. I'm going to kind of skip on some of the details just so that we can deal with my handwriting. That is meant to be a parabola, so an x squared, something, something, something. And we can see that it's decreasing on the left, it's increasing on the right. I didn't ask for any of that stuff, but we just want to know the relative extrema, relative maxima, relative minima. Well, this is enough information to talk about that. This point right here is where our extrema is occurring. There's only one for this one. That's the only hill or valley in this problem. This thing is going up forever and ever and ever. It has no absolute maximum, but it also has no relative maximum because there's no hill. This right here is a relative min, our min, relative minimum. So we can say that the relative minimum occurs at, and remember that's supposed to be the x value, that is the x value. Now this x value is sitting on the y-axis, it's not moving left or right at all, so that's 0. So that occurs at x equals 0. The actual relative minimum is, now that's supposed to be the y value, and the height of that point, and the only height I actually illustrated here, that's -8. -8. So the minimum occurs at x equals 0. The minimum is -8. Those are our answers for example 2A. Please note there are some there's some other words. You might see the words local. That means relative. So if you ever hear me say local min instead of relative min, or another teacher say local instead of relative, it has the same interpretation, tomato, tomato. All right, B. This one's going to take me a little longer to illustrate, a little more detail. So we're going to come up like this, back down, back up, and down. And I'm just gonna list these off as points, again, in the interest of not trying to jumble up too much information with new technology. So this point over here, I'm gonna say is 1, 6. This point here, we're gonna call 3, -4. That's a -4. And then this point right here, we're gonna call 8, 2. And those points should all make sense relative to each other. The left of the 3 points is the highest, the middle one's the lowest. The one on the right is the furthest right, so it should have the largest x value, et cetera, et cetera. Okay. So, text. We definitely have some relative extrema. We definitely have some relative maximum. We definitely have a relative minima or minimum. Maybe it's singular. We got two hills. Hill, hill, the 1, 6 and the 8, 2. And those are the tops of hills or our peaks. Those are our relative maxima. So the relative maxima occur at, and let's keep these in order. So x equals, the first one is 1, and the second one is 8. Those are the x values for the highest points, the 1 and the 8. They occur at. The relative maxima are plural. So the first one, the 1, has a y value of 6. So its relative max or maximum is 6. And if you want to write y equals, you can. You can write y equals. You can just write the value. It doesn't matter. So that would be y equals 6. And then the other one would be y equals 8, 2. The y value is 2. So y equals 2. For the minima or minimum, we're looking for valleys or troughs, and we're right here, kind of like the stock market, ha, ha, ha. So the relative minimum is going to occur at the x value, which is the 3. The minimum, singular, and if you were doing this by hand, I wouldn't care if you mixed up the singularness or pluralness of them. I hope that's obvious. So the relative minimum occurs at x equals, and that's a 3. The relative minimum is, and again, that's the y value, and I'll write the y this time to, again, emphasize it. That height is -4. I know that 4 got a little ugly, but that's a -4. So that is relative extrema. And what's interesting is it's a concept that you are going to pursue in calculus. And of course, things will get a little hairier in calculus, but the main idea is really just the same. You're looking for the tops of hills and the bottoms of valleys. You just have to do it a little more analytically in calculus class. You're not necessarily staring at the graph ahead of time. All right. So with that being said, let's move on to what we call piecewise functions. And I don't want too much information up here at once, so let's just push that aside. Piecewise functions. Piecewise functions give 2 or more functions that you use depending on what the x value is. Each piece will have a defined interval for x in which it's valid. Let's focus on that first, the line and a half, I suppose. We have seen graphs for a piecewise defined function before. If you go back to your notes from this section to example 1b, and I'll, not share, annotate. It was a graph that looks something like this. Up, and then we were flat, and then we were up. I'm ignoring all the numbers, but this was what the graph basically looked like for example 1b, and we talked about whether it was increasing, decreasing, constant for specific domain values. This is a graph of a piecewise defined function because this region over here would be the graph of a line. Then this region over here would be the graph of a different line. And then this region over here would be the graph of a third unique line. Let me do it this way. I'm just kind of doing vertical dotted lines to show you the separation. So to the left, this is one equation. In the middle, this is another equation. And to the right, this is a third equation. So there's three different equations that are governing this, this graph. But you can't just say, oh, here's your three equations. If you did that, this first one would extend all the way up. The middle one would extend all the way left and right. And this one would extend all the way to the left. And it would be a big jumbled mess. What we're saying here is that at a certain point, the function changes so drastically that we need a brand new equation for it. And then again, here it changes so drastically that we need a brand new equation for it. So you end up with things that kind of look like this. And these are not going to be very accurate. It might be x plus 1 for x's less than, I don't know, -3. And then let's say this is just a -4 from -3 to maybe +4, and then maybe an x minus, I don't know, 7 for x is bigger than 4. This is what a piecewise defined function looks like. So this top one, that's the left segment of the graph. This was the middle segment. And then this would be the right segment. And they don't have to go in this order. I can put the right one on the top. I can put the middle one on the bottom. It's just how I happen to do it with the intervals. So x is less than -3. That's about here, everything to the left. So we're using this x plus 1 graph when we're over here. But then it says when you're in this region of x values, that you're just going to have a constant height of -4, which is this. It's a flat curve. And then when we're to the right of 4, when our x values are bigger than 4, we instead use this one, which ends up looking something like that. And these numbers are all just kind of thrown not randomly, but they're just close. So this is what a piecewise defined function looks like, but we're not normally going to be given the graph and have to come up with this. That would be much more challenging. We're normally given the function, and then we have to create the graph. And then this note right here, it is a good idea to plug in the boundaries for each piece, even if it isn't included. Make sure to use an open circle if it isn't included. We talked about when to use open circles in class. I know it's been a couple weeks, but that's when you don't have an or equals. When you have the or equals, you use a closed circle. Sorry if you can hear me drinking my water. So let's try this out. Let's clear the screen. Go back to the whiteboard. And new page. So example 3. This will be A that we're going to do in a second. Graph piecewise function. So for A, we're going to have f of x is equal to. So this little curly bracket, it's not always used for these piecewise functions. If you just see something on top of each other without the curly bracket, it still means the same thing. So we're going to go x plus 3 when x is less than or equal to 2. And we're going to go 1 when x is bigger than 2. So again, without that curly bracket, this is still the same thing because I see these on top of each other, f of x equals, and it would probably be a little tighter, a little closer to each other vertically. That still means the same thing. All right. So let's set up a table of values for the first one. X, y. So we're using the x plus 3. But this is only valid for values less than or equal to 2. So if I can't plug 3 into that, I can't plug 5 into that, I can't plug 1,000,000 into it, I can plug any negative number into it, I can plug 0, I can plug 1, I can even plug 2. So let's do x values of 0 1, and 2. I'm just going to pick 3x values. Technically, you only need 2, and we'll get into that in the next section. You should have already understood that from graphing lines previously in other courses, but we will recover it. And if you plug these in, f of 0 would be 0 plus 3, which is 3. F of 1, oops, I have a button on this pen that I always accidentally click. Would be 1 plus 3, that's 4. And f of 2 would be 2 plus 3, and that's 5. So we have 3 coordinate pairs that we can go to graph. And let's go ahead and do that over here. I'm going to save some room on this space to do the second chart. How much room? I think this will be plenty. That's a little slanted, isn't it? Let's try again. There we go. Much better. It's kind of weird not looking where you're writing. So we got points of 0, 3. So that's up 3. Then 1, 4. So that's right 1, up 4. And then right 2, up 5 for the third point. That got a little high there. Let's try again. So again, that's 1, 2, 3, 4, 5, 1, 2. So there are 3 points, and it looks like we're making a line here. That's exactly what we're making. But this is only valid for anyone catch what I did wrong? This is what happens when you try and no, that's right. That is right. Never mind. I'm sorry. I just saw a negative in my head because of the or equals. Please forgive me there. All right, those points are correct. So this graph is only valid for x is less than or equal to 2. So I'm not going to continue this trend moving to the right of 2. We're only going to continue to the left. So let's see if I can make this as straight as possible. There we go. So there's our line. No mistakes made. I was wrong. So this is the first graph. Let me switch my color. And for the second one, which the output is just a 1. Now, there's no x's there, which means there's nothing to plug in. So this is only valid for x values bigger than 2. Now, I made a memo earlier that said you should plug in the border even if it doesn't have the or equals. I'm going to put a little star next to this point because it's the interesting one for all of them. I'm going to plug in 2 even though I'm not supposed to. I'm also then going to do 3 and 4. So that's the 3x values I chose this time. But when you go to try to plug it in, there is no x to plug it into. So the output is always just this number. When you plug in 2, you get 1. When you plug in 3, you get 1. When you plug in 4, you get 1. This is an independent function. It does not depend on your input values. It's always a height of 1. But again, this first one, it did not have the or equal, so technically we're not supposed to be plugging 2 in. This is an open point, the one that we have the asterisk next to. So when we go right 2 and up 1, I don't want to do a solid point. I want to do an open point like that, an open circle. And then let me switch back to black for a second. We got to go right 3 and 4, right 3, right 4, back to red. So the next point is 3, 1, which is right here. The next point is 4, 1, which is right here. So those are the 3 points of that line. And now we're going to connect them and only extend them to the right because this thing was not valid for numbers less than 2 or even equal to. It's only valid for bigger than 2 to the right. So what this graph does, it's just horizontal and it keeps moving like that. So this is a piecewise defined function. We have a very different line on the left and the right. Now I just made these 2 colors to show you where everything came from. This is all the same graph, Again, this is the same function. It just changes drastically at a certain point, kind of like our stock market just did. You'd probably need two different functions to model the stock market before and after COVID-19. So this is still a function because it passes the vertical line test, just as an FYI. You might say, oh, it fails right here. But remember, sorry, I went a little off track there. If you hit a solid point, then an open point, the open one doesn't actually count. So this is okay. It is still a function, which we'd hope so since we were told it was a function to begin with. All right. Let's do another one. Black. B. Example 1, sorry, example 2. No, example 3B. Did I call that example 3 before? I did. Good. Example 3B. Let's go f of x equals, and again, whether there's curly brackets here or not, it's the same thing. 2x minus 3 for x is less than 0, and x minus 3 for x is bigger than or equal to 0. So again, two different line segments, and these will both be lines, spoiler alert. They don't have to be lines. They can be parabolas. They can be all sorts of other polynomial, rational, compound functions. Anything is possible. You don't have to just have two of them. You can have three of them, as I described from the example 1b that had that flat section in the middle. So there can be a third one. There can be a fourth one. There can be a fifth one. We just generally don't get that complicated in here. There are, in fact, piecewise functions that have infinitely many of these different intervals. One of them is known as the Hessian function or the step function. But we're not going to cover that in here. Just fun little extra knowledge. All right, so 0 is where everything is changing. If any number that's less than 0, you're using the top one. Anyone that's bigger than or equal to 0, you're using the bottom one. But remember, we'll also plug the 0 into the top and just use that open circle. So for the first function, that looks like a exclamation mark. That's the 2x minus 3. Again, table of values. And we need numbers that are less than 0. So let's go -2, -1, and 0. Now this last one, I'm going to asterisk because it's special. It's going to be an open point because I'm not supposed to plug it in, but we still need to see what happens at the border. So f of -2, that's going to be 2 times -2 minus 3, which is -4 minus 3, and that's -7. So that outputs a -7. F of -1, that's 2 times -1 minus 3, which is -2 minus 3, and that's -5. F of 0, that's 2 times 0 minus 3, which is -3. Sorry, I got a little uneven there. So there are our 3 points. Let me go ahead to the side and start graphing that. Now remember that that last one is an open circle. I'm going to need a little more of the bottom on this graph. So let's, that was bad. I do not envy digital artists right now. All right, and I'm going to end up using positive x values of 1 and 2. So let me just go ahead and go from -2, -1, 0, 1, and 2. The y values we have so far are ranged down to -7. So let's go -1, -2, -3, 4, 5, 6, 7. I'm just going to label that bottom one for now, or let me maybe even label the odds. 5, -3, -1. So -2, -7, that's left 2 down 7, which is right here. Then we got -1, -5, that's left 1 down 5, which is here. And then 0, -3, which is an open point. So I'm going to do it this way. So there are our 3 points. Now these are valid for x's less than 0. Someone just asked, how do you know when it's an open circle? Because of the lack of an or equals. So for this 2x minus 3, it does not have an or equals here. And since I'm plugging the 0 into something that, again, I technically shouldn't because of that, that's how we know to use an open circle. When I go to plug it into the x minus 3 for the next part, because of the or equals, we don't have to use an open circle. Okay. So connecting, making a line, making a line, making a line, keep extending it, doing my best. There we go. So there's the first segment. Let's switch our color. Again, same graph, just using a different color for emphasis. So for the second one, that's the x minus 3, table of values. Longer. Let's go 0, 1, and 2. And again, 0 here will not be an open point. Plugging in 0, that's 0 minus 3, which is negative 3. F of 1 is 1 minus 3, which is negative 2. F of 2, that's 2 minus 3, which is negative 1. So our points this time are 0, negative 3, 1, negative 2, and 2, negative 1. Now, I want to flip back to the previous example for a hot second. When we switched to the second graph, we ended up with a solid point up here from the first one, and the second one had an open point down here. This is what's known as a discontinuity. If I wanted to draw this in one fell swoop, I would have to lift my pen off the paper, drawing tablet, whiteboard, whatever. I'd have to lift it up and then start down here. So I mentioned that because look what happens here. 0, negative 3 is literally the same point over here. But for this one, since it's included, now I get to go back and fill that point in. An open circle has now just become closed. That can happen sometimes. That happens when a piecewise function is not discontinuous. Some of them are discontinuous, some of them are continuous. And that is another important study in, guess what? Calculus. So the next point is 1 comma negative 2, which is right here. And the next point is 2 comma negative 1, which is right here. It's just another line, but it's a little flatter. Now this is only valid for positive values, so I'm only drawing this line to the right. Sorry, it got a little squirmy there. I'm doing my best, So there we go. So there is no discontinuity here. So if I wanted to draw this in one fell swoop, I can draw the black part, and then I stop for a split second, but I don't have to lift my pen. I can then draw the red part. This is a continuous piecewise function. It's got this weird little jut here. It changes directions extremely rapidly, which has complications in calculus, but we're not there, so it doesn't affect us. So again, functions can be discontinuous when they're piecewise, like example A. They can be continuous, like example B. It just depends on the nature of the problem. Alrighty, so that's piecewise defined functions. Back to the text. And just this one. Now we're here. This is a formula that in pre-calculus you will not have to memorize. When you get to calculus, you will have to memorize it, at least if you had me as a teacher, and I imagine most calculus teachers would make you memorize it. It's one of the most fundamental aspects of calculus, in fact. If I saw a calculus teacher not making their students memorize this, it would kind of scare me, honestly. So this thing, this f of x plus h minus f of x all over h, we call the difference quotient. Do you know why we call it the difference quotient? Because this right here is a difference, this minus, and it's a fraction. Fractions are called quotients. Just another name for fractions, divisions, quotients. The answer to a division is a quotient. The answer to a fraction, if you divide it, is a quotient. So we call this a difference quotient because in the formula, there's a difference and a quotient. Now, I could call the formula for slope a difference quotient. In fact, maybe it relates to that somehow. Spoiler alerts. Sorry, getting tangled in my wires. But this is a very specific difference quotient. And this f of x plus h thing, we've seen that before. Back when we started doing function evaluations, we showed what f of x meant and that you just plug in the number or letter or thing that's inside of it. So if I want to do f of 3, I turn the x's into 3s. If I want to do f of z, I turn the x's into z's. We did at least one example where we wanted to do an f of x plus h. So we turned our x's into x plus h's. And there was a decent bit of algebraic mechanics we had to deal with. It usually involved having like a binomial square and foiling and combining like terms and etc. And that's just one part of this problem. Because then you got to subtract f of x and divide the whole thing by h. What is h? Don't worry about it for now. You'll find out in calculus. I'll spoil it though. H basically turns into a 0 after you do all this work in calculus, not in our class. Again, not in our class. Don't make your h's zeros. That's a calculus thing. So what's the process for this? We have to give you an f of x. We have to give you an f of x. We can't not give you an f of x. Otherwise, how in the world would you ever find f of x plus h? The first thing you do is, well, find f of x plus h. So you'll do some side work, figure out that. And then what you'll do is you'll plug it in. So whatever you come up with for f of x plus h, you'll plug in right here. Sorry, I'm trying to highlight. Then you'll go minus, and you'll plug in whatever the f of x is. And then you'll write a big division bar, and it's usually a pretty big fraction. And in the bottom, you just write an h. And then from there, you're just going to do your algebra and arithmetic as best as you can to simplify this, simplify this, simplify this. And we can generally simplify these a ton. So let's try this out. Wrong thing. Whiteboard. So I'm going to write that difference quotient at the top. Oops, there's my button. DQ. F of x plus h minus f of x all over h. Now again, in your test, that will be built into the question. You do not have to memorize this, but you have to know how to handle the examples. So for example 4, we're going to calculate the difference quotient. I'm abbreviating difference quotient. And for a, we got f of x equals 2x plus 3. So that's our function. It's a line. It's actually pretty similar to some of the parts we saw from the piecewise functions in examples 3a and b. We had a 2x minus 3. This is a 2x plus 3. Not that that matters. But it's a graph of a line. And what we want to do is find this random difference quotient. So the first thing you got to do is find f of x plus h. Now this says we're taking x plus h and plugging into the x. So this original f of x, I'm going to write it in, I'm going to go back to red for a second. That was 2 times the x, and I'm going to leave this out for a second, and then a plus 3. So I'm not writing the x's from the original function. It was 2x plus 3, so 2 times something plus 3. But this is no longer an x. We're supposed to be plugging in x plus h. So this x in the original function, we have turned into x plus h. The reason? Because that's what it says to plug in. If this said f of 7, then this black ink next to the red ink would be a 7. Okay, well, we can clean this up. Distributing the 2, that gives us 2x plus 2h plus 3. That is the f of x plus h. That's this bit right here. So we're going to plug into there. I want to undo that so I don't make it too messy. Okay, so our difference quotient is equal to the f of x plus h, which is the thing we just found, the 2x plus 2h plus 3. That's this. Then there's the minus. I'll switch back to red. And then after that, we're supposed to use The original function, now this is always given to you. The thing after the minus is always given to you. We have to give it to you. That was this, the 2x plus 3. Now I'm going to start writing this incorrectly. And this is where if I was in class, I would ask why, but I can't do that. So this is wrong because we're supposed to be subtracting the entire function, and this is just showing a subtraction of the first term. So we have to wrap it, you may have guessed, in parentheses. This is extremely common for the f of x bit, extremely common. I would say almost every problem I ever do, you end up having a minus and then a parentheses here. And then all over. And the bottom is just an h. What's h? It's h. Just a letter. All right, well, we can definitely clean this up. We can distribute that negative. So that's going to be a minus 2x and a minus 3. So our difference quotient, let me switch to black now. That equals 2x plus 2h plus 3. Nothing happens there. There's no like terms. Minus 2x minus 3 all over h. Now, what happens in 95, 97, 99%, some very large percent of these problems, you're going to see a ton of cancellation here. Not everything, but a ton. You got a 2x and a minus 2x. So those are going to go away. Those are gone. We also have a positive 3 and a negative 3. Those are gone. So the only term we're left with in the top is the 2h. And then this is over. The thing in the bottom we never mess with, we generally don't. That's an h. But guess what? If you have an h on top and bottom of a single fraction with no pluses and minuses, we can cancel those. And that's going to give us an answer, an extremely simple looking answer considering the work we did of 2. So the difference quotient for 2x plus 3 is 2. Now here's what's fun. That problem took us a few minutes to talk out, and after practice, it still might take you a minute or 2 minutes. But I can tell you the answer to that in a quarter of a second. I know the answer is 2 because this number right here is a 2. And that's because this is a specific type of function. This is a linear function. So I'm going to make a little extra note here. Note that this is linear. And I'm begging the question a little bit since it's something we'll cover in the next section. But I imagine that a lot of you remember that the slope of a line is the number in front of the x if it's solved for y or if it's in function notation. So that 2 right here is 2. That 2 is 2. That 2 is the slope, and the answer is 2. That's not a coincidence. If this number right here had been a 7, the answer would have been 7. If this number right here had been a 14, this answer would have been 14. Now, that doesn't say that you can skip out on this work because this is a very special case. In fact, the difference quotient relates directly to slope. That's what you'll study in calculus. I'm not going to take it much past that, except in the next example to show you where it might be useful. Okay, so let's try another one of these, and let's try it with a more complicated problem. And I'm wondering if I have enough room. I probably don't. Let's make another whiteboard. Another reminder that difference quotient was f of, I don't like that button, x plus h minus f of x all over h. That's our difference quotient. So for example, B, let's do the function x squared plus 3x minus 5. So we just said the difference quotient relates to slope, somehow having to do with calculus. And we know about slopes of lines, at least I argue we should already, even though we'll talk about it in 2.3. This is not a line, this is a parabola, this is a quadratic. Their slopes are changing at every single point. Lines have a constant slope. Their steepness never changes. Its steepness is always changing. So the slope at one point is not necessarily going to be the slope at another point. There's actually an equation that dictates this function's slope. And this difference quotient is how you get it. All right, so the first thing we got to do, and I'll show another color for now. First, we got to do f of x plus h, which says we're replacing the x's in the function with x plus h. So I'm going to end up needing a parentheses here because I'm plugging in a binomial. Instead of x squared, it's now x plus h squared. So I'm using the red ink to show the substitution. Then we have the plus 3 times the x, which I'll put it in just a second, and then the minus 5. So the 3x turns into another 3 times x plus h. Again, the red ink is us plugging in the thing into x. We're plugging in x plus h because that's what this says. If this said f of 100, this red ink and this red ink would be 100. We're plugging in binomials, which you almost always need parentheses for that, just like in the last example. Now we're going to have a little more work to do for this problem because this x plus h squared. So let me just go to the side here so I don't have to rewrite a lot of things. This x plus h squared, well, that's x plus h times x plus h. And then you have to FOIL this. Remember, a lot of people like to skip foiling things like that. They just want to say it's x squared plus h squared, and that's completely wrong. You're missing half the work. So foiling that, the x times the x is x squared. The x times the h for the outer would be a plus xh or hx. Then the inner ends up being an identical product, h times x. And we've talked about in class how we should keep these in the same order, not mix them up. So let's go xh again. Then plus, for the last, we have h times h, which is h squared. They're like terms. xh plus xh. It's like having apple plus apple, which would be 2 apples. That's x squared plus 2xh plus h squared. It doesn't matter the order of the x and the h. If you prefer to write 2hx, because that's alphabetical order, be my guest. So this is what I'm going to plug into the parentheses squared, because that's what this is. So equals x squared plus 2xh plus h squared. I meant to change colors. Oh, well, it's all right. Then we're going to distribute this 3. So that's a plus 3x plus 3h. And then we're going to leave the minus 5 alone. You don't have to do this work to the side. It's just you would have kept having to write the plus 3x plus 3h minus 5 a couple extra times. It's arguable which one's better. It depends on how you like to do things. And at this point, we would try and combine like terms. But x squared doesn't have a like term. This is the only term with an xh. This is the only term with an h squared. This is the only term with an x, only term with an h, only term that's constant. This is as simple as it gets. And in fact, when we did one of those f of x plus h's back in the first section, we saw something very similar to this. All right, so now we can go back and do our difference quotient. So difference quotient. That's the f of x plus h, which is all of this red ink that we just found. So I'll keep it red to show the substitution. So that's x squared plus 2xh plus h squared plus 3x plus 3h minus 5. Again, that is just the f of x plus h. That red ink is just the f of x plus h. Then there's the minus in the parentheses, minus, and we're going to need a parentheses again because the f of x has multiple terms, and that's what we were given, that's what we were prescribed, the x squared plus 3x minus 5. And then this whole thing is over. I got to be very careful. H, all over h. It is very common for students to miss that h in the bottom. And the funny thing is, well, it's not funny, but that's one of the most important parts of the calculus. So equals. Well, we're going to distribute the negative. So all that red ink, I'm now just changing colors. X squared plus 2xh plus h squared plus 3x plus 3h minus 5 minus x squared minus 3x plus 5. Watch your distributions. All of those signs should be changing. And that should be all over H. All right, combine like terms. X squared minus x squared. They're going to cancel. 2xh, I don't see another one of those, so we leave it alone. H squared, I don't see another one of those, so we leave it alone. 3x cancels with the minus 3x. 3h, I don't see another one. Minus 5 cancels with the plus 5. Almost all the terms in the top are eliminated. And if you notice, both the first and the second problem, all of the terms from the f of x have gone away. That happens pretty much all the time. It happens for all polynomials. I don't want to say it happens for every single type of function in the whole world, but it happens for all polynomials. So we still have the 2xh, we still have the h squared, we still have the 3h, we still have the h in the bottom. Let's see what we got. So let's get back from that neon color. So that's 2xh plus h squared plus 3h all over h. And then you can simplify this because there is an h in every single piece of this fraction. All the different terms have an h. If any of them were missing an h, we couldn't simplify this necessarily, at least not in the way we're about to. So let's factor the GCF of h out. Go over here. That's h parentheses. If you take the h away from the first term, you're left with 2x plus. If you take a single h away from the middle one, you'll be left with 1. H squared divided by h is h plus. And the 3h, if you take its h away, you're left with 3. Close it. All over an h. And when we do this, we can eliminate the factors of h. This h is factored in the top. This h is a factor of the bottom because there's no pluses or minuses. So they're gone. So what we end up with is 2x plus h plus 3. And that is our final answer. Again, fairly simple looking in terms of what you might have thought the answer would look like in the process of the problem, because, oh man, look at all this, look at all this. This gets really big and ugly for a minute, and then it simplifies, again, quite a bit. So this is a function that relates to the slope of x squared plus 3x minus 5. The only thing that's weird in here is the h. And in calculus, I think I mentioned this already, but basically in calculus, you would just take this thing and make it a 0, and you get 2x plus 3. This isn't calculus. Please don't change your h's, but that's basically all you're doing in calculus. So 2x plus 3 describes the slope of this function. It's kind of interesting. What's even more interesting is in calculus, you learn a way to do this even faster. So I mentioned earlier the last problem that most of you can figure out the answer in about a split second. This one you can as well, but there's stuff to do, this x squared and the 3x and the 5 to be able to get this. And we're not going to teach that in here because this is pre-calculus. This problem right here is one of my favorite style different quotients. And what I mean is a quadratic, because you have to handle this x plus h and squaring it and foiling it and knowing how to combine the x h's. It's got a decent amount of work here without being overly difficult, I suppose, or just having too much stuff. And it still simplifies to a nice, in my opinion, simple answer. Difference quotient, very, very important in your math careers continuing forward. All right. Oops. Let's talk really quickly about symmetry. And this is going to relate to the next topic that you can kind of see at the bottom, even and odd functions. Symmetry is when a graph has a mirror somewhere, or you could draw half of the graph and then the other half of the graph would be very easy just to carbon copy. Imagine that you drew the right side of a parabola. So this is the graph of just x squared really, really quickly, but I'm only going to draw the right half of it. So here's the graph. It's not a great parabola. Let me try a little better. That's a little better. So this is y equals x squared, but I've only drawn the right half of it. What I'm saying is that if a graph has symmetry, if you know that this graph is symmetric, in particular it's symmetric about the y-axis, imagine that the y-axis, you are going to fold your piece of paper across it. So when you fold your piece of paper, if your ink is wet, it would make this image here by the wet ink. So again, your mirror, switch colors, is right here. This is symmetry about the y-axis, because this is the y-axis, this is the x-axis. The y-axis runs vertical, x horizontal. So if your y-axis is the mirror, then that's y-axis symmetry. You can also have graphs that are symmetric about the x-axis. So here's another parabola just tilted on its side. Now this is not a function, but it's still a graph. There's still an equation that models it. So this would demonstrate symmetry about the x-axis. There's our mirror. So symmetry about the y-axis means the y-axis is the mirror. It means the left side mirrors the right side. Symmetry about the x-axis means top and bottom mirror each other. It means the x-axis is where your mirror is. Symmetry about the origin means that the x and y-axis are both mirrors. Now, I need to clear these just so I have a little space here. But here's what here's a graph that would have symmetry about the origin. It keeps, just ignore that little error. There's a mirror there and a mirror there. So you would transpose this image to the left and then to the bottom, and you'd get down here. Or you can start with the bottom image and transpose it right and then up, and you get here. Or you can go up and then right. It doesn't matter which one you mirror first. But basically, the top right goes to the bottom left, or the top left would go to the bottom right. So it's a double mirror. So we're going to use symmetry a little bit later in the semester. For now, we're just going to go ahead and call it a day for the description there. But even in odd functions relate to symmetry. We're just not going to see any examples, just directly like, hey, is there a symmetry here? We're going to talk about something a little different. So even in odd functions. We have even and odd numbers. We also have even and odd functions. Not every number is even or odd. 2 is even, 3 is odd, 4 is even, 5 is odd. But 3.1 is neither. 3.9 is neither. 3.2 is neither. 3.78432 is neither. Even numbers and odd numbers are limited to your wholes, your positive and negative whole values. There are way more, there are way more numbers that are not even or odd than there are even and odd numbers. Functions can be even, odd, or neither in the same manner. And in the same manner, there are way more functions in the wild that are neither even nor odd than there are even and odd functions. So how can we tell if a function's even when we're looking at it as a function versus a graph? Even functions are such that, mathematician's favorite phrase, f of negative x, I told you we'd be plugging in a negative x back in chapter 2, 2.1, is equal to f of x. In other words, if you replace x with negative x, and in the end, everything looks exactly the same, your function is even. That says that positive inputs lead to the same thing as negative inputs of a symmetric value. Odd functions are if you plug in a negative x to your function, whatever you get is the same thing as if you just changed the sign of all terms in the function. This negative in front of the f of x, you might barely just be able to see. Let me do that. Means you have a negative and then you wrap your function in parentheses and you distribute it. So there's two things you have to do to check if a function's odd. There's only one thing you have to do to check if it's even, because the even function compares it to the original function. Checking for odd means you're comparing it to the opposite of the original function. So the process is, first, find out what f of negative x is. Turn your x's into negative x's. If it's the same thing as the original function, boom, it's even and you're done. If it's not, what you have to try doing is go back to the original function and just put a negative in front of the whole thing. If that answer ends up being the same as the f of negative x, then it's odd. In relation to symmetry, even functions are symmetric with the y-axis, whereas odd functions are symmetric about the origin, which was the double mirror situation. So even functions have a symmetry across the y-axis. It means the left side mirrors the right side. Odd functions means that the top right mirrors the bottom left, or the top left mirrors the bottom right. Notice it doesn't say anything about just mirroring across the x-axis, and I think that that should make sense because anything that mirrors across the x-axis would not be a function. Just really quickly, let's draw that image from earlier really quickly. So this is mirrored about the x-axis. It's certainly an equation, it's certainly a graph, but it's going to fail the vertical line test miserably. That's not a function. So how could anything with x-axis symmetry be a function? Even in odd functions have the word function in them. So something that's symmetric about just the x-axis is not a function. So here is that basic x squared again. This graph would be even because it's symmetric about the y-axis. Here's the graph of, spoilers, x cubed. And the upper right is a mirror of the bottom left. This is an odd function. It's symmetric about both axes. It's a mirror across both axes, that is to say. So let's try this out. Let's go to our whiteboard. Page. Well, we're up to example 5. Even, odd, or neither, also known as neither. Ha ha ha. Even, odd, or neither. For A, let's do f of x is equal to x to the fourth plus 5x squared. So what we have to try is f of negative x. So if our function's even, then by plugging in negative x, we'll get the same exact thing as the original function. So this is going to be x to the fourth, well, that's now negative x to the fourth, plus 5x squared, but that's now a negative x squared. Okay. But when we have a negative raised to an even power, it always becomes positive. This is also a negative raised to an even power. So this is also going to become positive. So this is going to be x to the fourth plus 5x squared. And if you compare x to the fourth plus 5x squared, this is the same thing as the original function. So this function is even. We turn the x's into negative x's. If you have a question, you can post it in the chat. So we turn the x's into negative x, but these negatives were being raised to an even power, which made them positive. If this had been a 3 as an exponent, a negative to an odd exponent is always negative. And we might see that in another example, spoiler alerts. All right, B. How about f of x is equal to, let's go with 2x cubed plus 5x. The first thing we have to try is the f of negative x. So all of our x's are going to turn into negative x's. So that's 2 times, in parentheses, negative x being cubed, plus 5 times, in parentheses, negative x. And a negative to an odd power is a negative, so that's negative 2x to the third. 5 times negative x is a minus 5x. And that's all we can do with that. And you'll notice this is not the same as the original function. It's close. It's got 2x cubes and 5x's in it, but the positives are now negatives. So this is not the same. Therefore, it is not even. So now we have to go to the next part of this process, which said to try out negative f of x, which means we take the original function and we just slap a negative in front of the whole thing. So I'm going to write the original function, which was 2x, wrong color, which was our 2x cubed plus 5x, but we're negating this whole thing. To negate the whole thing, we wrap it all in parentheses and put a negative in front of it. F of negative x is very different from negative f of x and how we process it. This is us plugging in a negative x for the previous bit. Now we're just putting a negative in front of the whole thing. But we can then distribute that. And when we distribute, we'll get negative 2x to the third minus 5x. Now that's not the same thing as the original function, but that's not what we were asked to check. Odd functions are when f of negative x is equal to negative f of x, which if you look carefully, this thing and this thing are the same. That's the same as f of negative x. Oops, I just wrote that incorrectly. Undo. Wrote my negative too soon. So that means the function is odd. Horizontal line test has to do with inverse functions. We'll get into that in 2.8. We have not talked about a horizontal line test yet. Someone just asked that in the chat. I was mentioning the vertical line test for functions earlier. All right, C. F of x equals, and let's go with, how about 3x to the fifth plus 7. 3x to the fifth plus 7. So we'll do our f of negative x first. with 3 times the x to the 5th. That'll be a negative x to the 5th now, plus a 7. And a negative to an odd power is a negative, so that's negative 3x to the 5th plus 7. So this is not even, because that is not exactly the same as the original function. It has to be exactly the same. So we try doing the negative f of x. So that's where we take the original function and just slap a negative in front of the whole thing. So 3x to the 5th plus 7 inside of parentheses with a negative in front of it. We distribute our negative, which will give us negative 3x to the 5th minus 7. That is not the same as what we just got previously. So the odd functions are when the f of negative x and the negative f of x match. They're close, but they're off by a sign, plus, minus, which means it's not odd. If a function's not even and it's not odd, that means it's neither. It's an interesting function. Now, some of you may have drawn a conclusion about what it means to be an even function or an odd function. Why are we giving them these names? And this is where I would normally pause for a minute in class and hope someone raises their hand and recognizes that, oh, A was even, and look at that, the exponents were even. There was a 5 here, which is odd, but that's a coefficient. It's the exponents that are even, and the function happens to be even. And then it'll go, okay, well, B has exponents of 3 and, you don't see it here, but there is a 1 that's implied. 3 and 1 are both odd, so that function's odd. But then you get to problem C, and you go, oh, well, I only see an odd exponent, and you might just snap your fingers and without doing any of the work say it's odd, and it turns out that it's neither. Now, admittedly, for the most part, a function being even or odd for polynomials does tend to agree with if all your exponents are even, it's an even function. If all your exponents are odd, it's an odd function. But constant terms will throw a wrench into those spokes, and it'll make a function that looks like it's odd not actually be odd, or it might make a function that's even or look even not actually even. And I'm not going to spoil that last part. The point is, you need to do this work. Yeah, there are shortcuts, and if you understand that this is kind of a special case, as long as you can get it right 100% of the time, then per usual, I don't necessarily care how you're getting it done. But I love problem C for that specific reason. So yeah, the general rule of thumb is even functions, even exponents, odd functions, odd exponents. But if you're not looking at a polynomial, you can't tell. There can still be even and odd functions for non-polynomials. Even some other weirder polynomials that might look odd are neither. Maybe a function looks even and it's actually neither. You need to do these evaluations. All right. And that will finish up 2.2. Okay, deep breaths. Let's move on to 2.3. Linear functions and their slope. Something that I mentioned several times already that we kind of beg some questions. Just to talk theory. A line can be formed by just 2 points. Yes, you can connect a line with 3 or 4 or 5 or 20 different points. And that's okay, but it's also more work than you really have to do. If you can look at an equation, if you can look at a function and you know it's a line, then you only have to graph 2 points. And you don't even have to use 2 x values to find 2 y values. You can graph 1 point and then use slope to find another point. And we will talk about that later. But any line can be formed by just 2 points, then you connect them and extend them. Every line has a constant slope that can be calculated, that can be found by calculating the rise over the run. Rise over the run. Slope being a measure of steepness. So the larger the value, the steeper the line is. Or if you're talking about a curve, because we will very, very, very lightly talk about slopes and curves, same thing. Lines that have a positive slope mean as you move right, you're going up, i.e. they're increasing. Lines that have a negative slope means as you move right, you're going down. Horizontal lines have a slope that's 0. Vertical lines have a slope that's undefined. That 0 slope and undefined slope, that's something that our Algebra 1 students will kind of pass over and forget all the time. You can't forget that in pre-calculus, surprise, surprise. We're going to be using that, I don't want to say super frequently, but we're using it enough that you need to remember those aspects. So, and I didn't type the formula for slope up here. That's all right. So what is our formula for slope? Let me put it, I'll put it up here. We use the letter M for slope. And it's y2 minus y1 over x2 minus x1. You have got to memorize that formula. And once you memorize it, what do I always say? You never get to forget it. You're going to be using it in calculus, and you'll use it in any math class after that. Slope is the difference of the y values divided by the difference of the x values. So this is the slope of a line going through points x1, y1, and x2, y2. Little numbers just tell you whether you're referring to the first or the second point. And it doesn't matter which one you call the ones and the twos as long as you're consistent. You're never going to have an x1, y2 or vice versa. Even in the slope formula, the twos and the ones are interchangeable as long as you're consistent. You can do y1 minus y2 over x1 minus x2. You can't swap the x's and the y's though. You can't do a 2 minus 1 in the top and a 1 minus 2 in the bottom. You have to be consistent. So again, that is your slope formula that you have to memorize. You have to memorize it. So let's show what positive, negatives, 0, undefined slopes look like. And let's very, very, very quickly do that on the whiteboard. All right. So again, m equals y2 minus y1. That's a terrible looking y. All over x2 minus x1. Here's a line with a positive slope. That's an m. M is greater than 0. Here is a line with a negative slope. Here is a line label the axes. Here is a line with 0 slope. Horizontal lines have 0 slope. And then here is a line with undefined slope. Undefined does not exist. It is both infinity and negative infinity at the same time. That's what it means to be undefined for us. It's kind of like dividing by 0. In fact, it literally relates to dividing by 0. So our formula for our slope, whether it's positive, negative, 0, or undefined, and let's use that to calculate some slopes. So for example, 1, A, and I do have a B as well, I just don't have it typed. We're going to calculate the slope of the line going through 3, negative 5, and negative 2, 7. I have a C as well. So 3, negative 5, and negative 2, 7. 1, 3, -5, and 2, was it -7? I believe so. No, -2, 7. 3, -5, and -2, 7. So if you want to label things, you can. You don't have to. But I would call the 3 the x1, the -5 the y1, because it always goes x, comma y. Then the -2 is the x2, and the 7 is the y2. So then we just plug everything into our formula, which we had on the previous screen, the y2 minus the y1. That's 7 minus -5. It's a double negative, so you have to set it up that way. Be careful. A lot of people just see that -5 and just write 7 minus 5. All over, excuse me. -2 minus 3. That's the x2 minus x1, which is 7 plus 5 over -2 minus 3. 7 plus 5 being 12. -2 minus 3 being -5. That's an irreducible improper fraction, but it's got a negative in the bottom, and nobody likes that. So please write that as -12 fifths. The negative out front or in the top. Do not leave negative factors like that in the bottom. Most math teachers are going to say it's not simplified. Let's do another. Here's our b. We got 6 comma 1, 6 comma -8. Again, should you choose to label them, I'd call the 6 the x1, the 1 the y1, the 6 the x2. Oh, interesting, that's the same number. And -8 the y2. So our m, the y2 minus y1, that's -8 minus 1. Watch your arithmetic, watch your signs. Excuse me, the x2 minus x1 is 6 minus 6. They were the same number. Coincidence. -8 minus 1 is -9. And 6 minus 6, well, that's 0. And we all know that 0 in the bottom is what makes the world go bad, explode, whatever you want to say. This is undefined. You cannot divide by 0. So guess what that means? Those points form a vertical line. Those points form a vertical line. That's what I just wrote very, very sloppily. I'm sorry. Because I got an undefined slope, I know those points form a vertical line. I can't say that about A. If I got an answer of 0, I would know the points form a horizontal line. For C, let's go with 1, 5 and 3, 9. We have a few minutes left. So once again, should you choose to label them, I find it helpful. x1, y1, x2, y2. Please feel free to swap the 1s and the 2s. You should get the same answer in the end. So our m is y2 minus y1, that's 9 minus 5 over x2 minus x1 is 3 minus 1. 9 minus 5 being 4, 3 minus 1 being 2, 4 divided by 2 is 2. Slopes can be fractions, they can be whole numbers, they can be positive, they can be negative, they can be 0, they can be undefined. Example 1a happens to have a negative slope, so as you move right, it's going down. Example 1c has a positive slope, so as you move right, it's going up. That's all we can really say for now. So we can calculate the slope given 2 points. We need the 2 points. We could also do this if I gave you an equation. If I gave you y equals 2x plus 3, you would just have to plug in your own x values, up to you completely. Me personally, I tend to use 0 and 1 because they're easy numbers to plug in. Find respective y values to give you a completed point, and then you can find the slope. For the last thing of the day, we're going to talk about one of the three formats of a line. There are three formats of lines, two of which are very important for us, one of which not really important until you get into higher mathematics, specifically math and 3D. And I mean, it's good. That third format is good for other things. If you're dealing with systems of equations, it's nice to have them in that format, but it just doesn't tell us information. Point slope form. So point slope form of a line. The reason we call it point slope form is because in it, we can see a point, the x1 comma y1, and its slope. So if you see something in this specific format, you can tell me what the slope is because it's the thing in front of the parentheses. And you can tell me a point it goes through because it's the number after the x and the number after the y. But those are minus signs, so you're flipping signs around. Also, if I give you a point and a slope, like in example 2a, you can put those numbers into the form and come up with an equation. So this format, which you have to memorize, surprise, surprise, y minus y1 equals m parentheses x minus x1. The y1 and the x1 are numbers that you'll plug in. The m is a number that you'll plug in. You will leave the y and the x alone. You are not plugging things into the y and into the x. Just the m, the x1, and the y1. Again, you have to memorize this format. It's called point slope form because in it you can see a point, the x1, y1, and the slope of the m. So for example 2a, we're going to find the equation of a line. This will be the last thing we do, going through the point 2 comma 3 with a slope of 5. Find the equation of a line going through the point 2 comma 3, that's our x1 and y1, with a slope of 5. And graph it, we'll get the graph later. So we'll get the graph next time. Let's just focus on the form. Oops, wrong thing. Share. That's 2 comma 3 and 5. Example 2, where's it 3a? It's 2. Sorry about that. Example 2a. So we're going through the point 2 comma 3 with a slope of 5. Again, we're plugging this into y minus y1 equals m times x minus x1. So from left to right, the m is obviously identified. The 2 is the x1. The 3 is the y1. The m is 5. We're plugging those three red numbers into the equation on the right. Nothing else. So the y stays the y minus. y1 is 3. Then our equals. The m, which was the 5, I'm just going to go ahead and put the parentheses up here, and then x minus. So again, the m was the 5. That's what goes in the front of the parentheses. Then parentheses x minus. And then the x1, which we said was the 2. And generally what we do at this point is solve it for y. This is technically an equation. This is the equation in point slope form. But most often we want this solved for y because it puts it in a cleaner format that's more consistent. Every equation of a line has got infinitely many versions in this format, but when you solve it for y, it's always going to turn out to be the exact same thing. That's y minus 3 equals 5x minus 10 when you distribute. Then we're going to move terms from side to side. We need to solve for y, so we're adding 3 to both sides. Which will give us y equals 5x minus 7. And again, that's the best format for equations. This is known as slope-intercept form. We'll talk about that more next time, as well as do another example, as well as graph it, but I don't want to take us over time. So we will call it a day there. Remember, your test 1, is in my math lab. It is due tonight by midnight. You've got 2 attempts. You get 2 hours for each attempt. I've only got 10 people who have completed it up to this point. Please do not take a 0 on this test. I'm not going to be given makeup opportunities for this. You have to take it today or that is it. I wish you all the best of luck with it. Um, thank you for tuning in. I know most of the class um, showed up for this, so that is excellent. Someone just asked, when will this video be able to be reviewed? As soon as I cut the stream, it's gonna take about 10 minutes to convert to a file that I can download. Then I upload it to YouTube, and it usually takes another 10 minutes from there to be live. I will have the link in Canvas set up in the next 10 minutes, but you might not actually see it take you to an active video for another 10, 15 minutes after that. So I hope that helps. And again, remember these videos are up here, so if I went too fast somewhere, go pull up the YouTube video, pause it. Um, Someone just asked about a quiz question. I didn't do any today, spoiler alerts, but again, those might be randomly just to make sure that everyone is watching the videos fully. So no quiz today, maybe next class, maybe the class after, I'm not saying. Thank you all for being here. Much love for you all. Stay safe, and I will see you on the internet in a couple of days.